Just the others. It was literally just the spider web.
Yes, like it's like you tell me about this file.
It's not more complicated.
I sort of control this.
We can just change the file.
It's great. So let's get started. So, so today we're going to kind of, so really in earnest start the lecture, the section on graphs in this class, which is the last section. We'll be talking about Markov chains. It's probably reasonable. You've seen some version of Markov chain before. We'll talk about them. And I think they're usually, depending on where you see them, there's usually two different versions of Markov chains. I'll try and cover both so you understand the kind of the two different ways you can think about them. Before we go further, I just want to remind everyone where we are in the schedule. It's kind of the crunch time of the semester. I know that. We're down here, close to the end. All right, so the first thing is homework 6B is posted. It's the graphs part of the noise and graphs homework. It's posted linked off of here. I don't think it's on Gradescope yet, but you can get started on it. We'll try and get on Gradescope soon. It shouldn't be too hard, and you should basically be able to do it after today's lecture. So hopefully it should be about half of an assignment. So hopefully it's pretty quick, even though I know everything is often due on the last day of this of the semester. It's only half of assignment in this course. So the dimensional reduction homework is being graded. It's almost done. We should have the results out soon this week. It's the end of the semester for the TA as well. So she's also kind of slammed. And I'm optimistic we'll get the noise assignment graded by the final, but I'm not sure. We'll try our best. If there's anything that seems that there's a lot of confusion on, I'll at least try and report that before the final. So we will obviously won't have this one graded for the final, but you'll have to do it before, which I think is the point, to kind of reinforce the knowledge from the lectures there. All right, I'll probably talk more about the final on the Monday beforehand, but it will look like the midterm, except it'll be on the second half of the class. Everything after the material covered in the midterm will be the focus of this of the interim. It could include stuff you see on Monday. Yep, it's possible. Yes, there's not a separate final test in the exam, although the poster day for your posters is technically the final. It's in the final slot. All right. The other thing is that the final report is due on Wednesday. All right, let me just review a couple things on the final report. All right, so first of all, it's 4 pages per student in the group. So if you have 2 people, that's 8 pages, 3 people, that's 12 pages. It doesn't have to fill that number of pages. You can also put more stuff in the appendix. Probably won't read this stuff in the appendix, but I will read all the reports. Single column and make the font at least 11 point with margins, so at least 1 inch. Again, I have to have all these rules because otherwise people don't follow all these rules. I've had reports that were 8-point font with 1/2 inch margins, and that's why I have to have these rules. But I do actually want to read all of it. If you have charts and figures, put those in the main body. That's the stuff I want to see along with the text describing them, right? So don't just put all the charts in the appendix. I won't see them there. I want them in the 12 pages of or 8 pages of content you have. What should the content include? It should have a title and your names. Okay, that counts as part of the 4 pages. kind of explain the problem and the motivation. Kind of your proposal intermediate report, you can borrow language from all of these things. And the data you explored can also borrow language from your kind of data collection report, right? Then I want to see what is the key idea, right? I want you to have done something interesting, something I will find interesting. Kind of highlight what is the key idea? How did you evaluate that idea? All right, so explain what you did. And it should be make sure that you use some techniques from class, right? So try and highlight whatever it was, the technique you use from the class. I'm looking to see you applying that on some actual data problem. With the intermediate reports and your feedback, we talked through all of this. I know all the groups have some strategy for how to do this. If you follow that feedback, you'll be fine. Okay, the last thing is the ethics evaluation. Okay, I want your kind of honest feedback on whether you kind of, there are any kind of ethical concerns that you might have with your work. We tried to do a practice of that last week on Wednesday in class. I feel like I definitely should have left an entire lecture for that. Hopefully it was a fun experience. We kind of crammed it into one half of a lecture. Next, I should have put that full lecture, but hopefully you got a sense of how to think about the ethical implications. Think of the pros and cons of what could happen if you were to actually deploy this, and then kind of you can decide. Do you think would this make sense to deploy, or would there be maybe too many kind of potentially harmful consequences of it that you think might kind of outweigh the beneficial sort of consequences of it, right? So I just want you to think through that. It's okay if you say, on second thought, maybe we shouldn't do this. That's great, right? Probably it'd be reasonable if one or so projects a year to decide to do that. Like in a lot of the data science conferences now, when you submit a paper on new research on it, you have to do an ethics assessment on it. So this is kind of a fairly becoming a mainstream thing to do. I think is a great practice just to pause and think about these things. Okay, any questions on the report due on Wednesday? Groups pretty much feel they're on track to finish? Yeah, okay, great. Yep. What does it say on here?
Yeah.
It says it's at midnight. Okay, great. Then it's due on some midnight on Wednesday. I know it's day before Thanksgiving. If you can turn in early, I guess, if you want to as well. But I'm just okay, great. So I'll look forward to seeing those. I should have read them before. Expect I'll have read them before the poster presentation. Great. So okay, so we're going to talk about the graph section of class. We're going to have 3 consecutive lectures on this. We also earlier talked about the graph clustering with spectral clustering, and we had half of a lecture on graph embeddings. That probably would have been better as the last lecture when we've seen some of this other graph material. So we're going to start with Markov chains. I think this is a really kind of core kind of idea that is important in analyzing graphs for when the graphs are representative data. This lecture will be more abstract in how we treat graphs. We won't think of them as modeling something specific. The next 2 lectures, we'll think of them very common cases where they're modeling like the web, the internet in various ways, and then in like in social networks, the last lecture next week. And so this lecture will kind of have a bunch of definitions in it and slides, and to kind of get less exciting if I'm lecturing with slides, but I will add some life lessons along the way. Hopefully these are interesting. I'll try and mathematically define what I mean by these throughout the lecture. Okay. So, you can understand the right. So this lecture is especially about karma, so watch out. All right. Okay. Yep. Okay, great. Graph, this is kind of my favorite example. Graph, again, were mathematically often presented to us with these vertices, which are these points, right? And then the edges, right? And so we can think of them as this ball and stick model of the graph. We can draw pictures, but we want to actually analyze much larger graphs that we cannot so easily draw a picture to think of and analyze. Okay, so a lot of the ideas make sense on smaller graphs if they're chosen carefully, but when you get to graphs, I don't know, you can probably get 10 times as big as this and still draw it fairly well. But beyond that, it starts to become not very helpful to draw it, despite there's whole communities on graph drawing. It just becomes hard once you get to more than like a few hundred nodes. Okay, and we're going to think today through a matrix style representation of the graph. Okay, and so this will be kind of key here for thinking about it. Again, this is typically not how it's stored, okay, but it'll be useful to think so we can apply linear algebra on this, but in a different way than what we've done before. Okay, so now we're going to be looking at, say, a particular node here, say node C, right? And we're going to have the graph we can represent as this as a column. Okay, and this column describes which other of the vertices is it connected to. C is connected to A, C is connected to D, C is also connected to E, right? And so it also has a 0 if it's not connected, right? So it's not connected to F, and you do not have an edge between C and F, right? So but this is a square matrix, so I also have the same information captured in the row for C, right? This is the adjacency matrix. So I can think of this as the adjacency matrix of the graph. Sometimes you will have directed edges, okay, where you can say a node goes from F to H, right? Then you would say it would go from F to H. Great. So you could also consider this node from H, this edge, this entry that describes from H to F, right? So, and if it's a directed graph, it may not be symmetric here, right? So I may have a 1 here and not on the other side. Okay, we'll deal with a little bit of the symmetric. We'll turn this into a non-symmetric matrix, but we'll be dealing with the symmetric properties of graphs. Okay, we'll assume that the graphs are pretty much undirected. Again, I mentioned for the most part, it can be, usually the analysis is not too different if you allow for directed edges instead of undirected edges. Great. So, okay. So, the key thing is we want to model a graph as, we're going to model the graph as we're going to model it as a Markov chain. Okay. And the Markov chain is going to consist of three things. Okay. It's going to have a set of states. Okay. These are called the states. Okay. In this case, the vertices is the node set. So these are all of the the vertices in the graph. Okay, it's going to have the probability transition matrix, okay, which is the probability transition matrix, which is this matrix here. And then the third thing is going to have an initial state Q, okay, which I will do, is going to be one of these options. All right, so the first one, the node set and the probability transition matrix are going to be defined directly from the graph. Okay, the node set is just going to be the vertices. The probability transition matrix is going to be derived from the graph. It's going to look like the adjacency matrix, but I've got a bunch of fractions in here instead of zeros and ones. Okay, and I've chosen, I didn't just randomly turn them into fractions. Some of them, I still have a 1 here. There are some 1/2, there are some 1/3. How did I choose to do this? The key is that I want to look at the rows, okay? And I want to turn this into from the row of A of if this matrix was called the adjacency matrix, which we talked about in when we were defining the Laplacian. So I'm going to take this column. Sorry, I think I may have said row. I'm going to take the column of the adjacency matrix, and I'm going to L1 normalize it. Okay, and remember, if I'm going to take an L1, let me just write this as a vector. A vector, and I take the 1 norm. This is going to be, remember what the 1 norm is. I'm going to j equals 1 to n of vj. I'm going to take it to the power. I'm going to take the absolute value of this to the power 1, and then I'm going to take this to the 1th root. Okay, there's the definition of a p norm. The 1 norm is where I use 1 for here and here, right? So these values, this value 1 is here and here, but those values aren't doing anything. So it's just the sum of the absolute values here. And I had it so all these values are positive, right? So what this does is so kind of this 1 norm, what it does is it's turned this into a probability. Okay, and what the probability is modeling, this was the one corresponding with state A. Okay, and so I'm saying that I'm in state A. Okay, and I'm going to go to one of its neighbors at random. And I'm going to put equal probability on each of these. Okay, I'm going to say 1/3 probability. If I'm at A, I'm going to move to node C, D, or B, right? And 0 probability of going to node E, G, or the other ones that it's not connected to as an edge. All right. So this is the standard way you would set these kind of you turn the graph into a probable move of a next step if I were to take a random walk on the graph. Okay, I could decide to set the probabilities in a way that's different, so it's not equal to each of them, but in general, you just say, okay, I'm going to say each node is going to be equally likely. All right, and so now I've turned this column into a probability vector. Okay, so the probability vector now, this is going to be in delta n. Okay, so this is a vector in Rn, where, so it's the vectors in Rn where for v in in delta n, I have Vj is going to be in between 0 and 1, and the sum over j of Vj is going to be equal to exactly 1. Right? So this describes a probability vector. This delta triangle n would be an n-dimensional probability vector. Okay, so this is what I mean by probability transition matrix. So it's the adjacency matrix where I L1 normalize all the columns. Okay, and the columns are describing what I do when I'm at the state corresponding with each of the columns. Okay, all right, so now the last thing I need to describe is the initial state. The initial state does not depend on the graph. Okay, and so the next kind of one of the next things we'll need to do is we'll have to figure out how to get rid of this because we want to analyze graphs. Okay, so so this doesn't have to do with the graph, but at some initial state, if I'm going to model effectively a random process on the graph where I'm randomly walking around on it, and so there are kind of two ways I can do this. One is I can say that Q, this state, tells me I should always go to B, right? So I'm saying I am initially starting in state B, that I'm going to do a random walk on the graph, and I'm starting in state B. I have a zeros except for a 1 in one position. So I'm starting in state B, and then I'm going to follow whatever's the distribution in this column to tell me where to go next, and then keep going in this process. There's another way of thinking about this where I write down a probability distribution here, right? So this is an element of delta n. This is a probability distribution. Now I have 10% probability of being in state A, 30% probability of being in state D, and a 6% probability of being in state so F, right? So I have 0.1, 0.3, and 0.6, right? So that's what this representation is implying. Right? So now I can say my state is probabilistic. I'm kind of representing where I am by a probability distribution. And so this kind of, I'm not in one position, I'm kind of in a quantum state, but with like a probabilistic notion of where I am when I'm doing the random walk. So I could be in any of these locations, but I'm more likely to be in F, and I have 0 probability of starting in state G. Okay, so my initial state could be either of these. Okay, and sometimes you want to restrict to this version, this purple version, where I'm exactly in one state at a time. Other times it's more convenient to be kind of spread out, and we'll kind of talk through this. Yep.
So this initial state is basically which node it's most likely to start at?
Yeah, so where I should start at. When I define a Markov chain, it's defined by these 3 quantities. The set of states, which are my nodes, the probability transition matrix, which in our case will be the L1 column normalized adjacency matrix, which tells me the random process from one state to other potential states, and then where I start the random process, the initial state. This is what defines a Markov chain. Okay, this is kind of a cool mathematical object that comes up in lots of places. Today, we're using it to analyze graphs. Okay. All right. So the cool thing about the Markov chain when we're treating this as linear algebra is that we can, as a matrix, is we can kind of enact and model this random walk through linear algebra here. Okay, by just multiplying our initial state, Q, by this matrix P. Okay, so if I set my initial state here, right, so I'm saying this is my initial state here, and I multiply it by the probability transition matrix, right? Then I'm going to get the state after one time step. Okay, in this case, I started the initial state, so I'm always deterministically starting in B. Okay, and what do I do? Well, half the time I go to A, and half the time I'm going to D. And so what it says is that I'm just saying, well, I started in B, and half the time afterwards I'm in state A, and half the time I'm in state D afterwards. So now my kind of probability distribution is split. Yeah.
So if you were to like have, I guess, better subscripts, you would say that the initial state would be Q0, and then this other one would be Q1.
Yeah, right. So I'll start initially at Q, sometimes I'll call it Q0. Thanks. Yeah. But then I'll have state Q1 after one step, and then we'll see what happens after the next step. And just keep multiplying it, right? So now after 2 steps, I do this. P has stayed the same, initial state has stayed the same. I have here, but now I get this matrix as the state after 2 steps, right? And so there are a few different ways I can compute this, right? So the first way of computing it is I can take the result Q here. Okay, and I can have this be pushed down, and then I multiply it by the probability transition matrix. This gives me Q2, so I'm in state Q1, and then I apply by Q2, and I get this updated state. I can also take the initial state and multiply it by P twice. Another way is I could take the probability transition matrix and I can square it. What this does, it then transforms it into what I would do if what happens if I'm in one state and I take 2 steps? What's the probability distribution of that? That's what P squared tells me. They all are going to give you the same result. This is linear algebra. All the linear algebra is the same here, right? Okay, and just to kind of make sure this is clear, I'm in state, I have half my probability in state A here, and then this is going to get pushed into, and the other half of it is in state D. Okay, and so now we can look at computing the output of state A. Well, I've got this here. I have 1/3 that points to state A, but multiplied by 1/2, right? So this is going to be 1/2 times 1/3. The next one is a little bit more interesting. I now, for state B, I get 1/2 from D and times 1/3 if I was in state D after 1 step, and 1/3 if I was in state A after 1 step. So now this guy is going to be 1/2 times 1/3 plus 1/2 times 1/3, right? And this gives me, each of these is 1/6. I get 2/6 of being in the state. The same thing happens for state C, and then for state D, I have just 1/3 times 1/2, right? And I haven't gotten to states E, D, E, F, G, or H yet. I couldn't have gotten those in 2 steps. So the probability of being there is 0. Okay, so this is kind of, but I can write it as linear algebra. All these will give me the same answer in this example. Okay, see one more example, right? Where we take another step. Now we've computed Q2, and I'm moving this into here, and I can map this down here, multiply by the probability transition matrix again, and my probability is spread out now. Now there's some probability of getting to state E, right? I could have gone from state D. There is from state C, there's a chance to get to E. So 1/3, the probability was here, and part of it leaked out. 2/6 is 1/3, and 1/3 of it leaked out. I get 1/9 here. Right, so now I've leaked out into state E. All right, so what we want to understand is actually what happens in the limit. right? What happens as I take n to be larger and I take more and more steps here, right? I take more and more steps of this Markov chain, right? What's going to happen? All right, so what do you think will happen when I take more and more steps? It will converge, good. Maybe, yeah. What? There's a loop, it might converge if there's a loop. There might be loops in here. Yeah, loops are things we have to worry about. We'll call them cycles, and we'll see what can happen with cycles. Those might be a concern. Will it get to 1/8? There are 8 states here. Okay, so will it get to this uniform distribution? Where after, if I do a random walk everywhere, I'm going to be equally likely in like all of the states. You think it's going to converge to this? No, you don't think it's going to be converged to this. Yeah. Oh, okay. So we have great. You're kind of coding this up as we're going. At great. We will not get to the this uniform state. There's going to be some states that get the same distribution in the so the same distribution in the limit, but it's in general not going to be this. You have to have a very special symmetric graph for it to be a uniform distribution in the limits. All right, you're instead going to get to some other sort of distribution, and that distribution in the limit is going to tell us a lot about the graph. Okay, and in fact, if we do this correctly, the state Q, the initial state we start with, is not going to matter, and so then it tells us something about the graph because it won't depend on what the initial state Q was. Okay, so this is kind of what we want to get to. But you're right, there are things, these loops and cycles we have to worry about, right? So we want to talk about when can we talk about the limit? Okay, and okay, so this first life lesson here. So this is the Markov property where this Markov chain models that where your next state will only depend on your current state, right? This is what kind of called like a Markovian process. And so that is what this is modeling here. It does not depend on where I was 2 steps ago. I just need to know where I am now, and that's all that's going to tell me about where I'm going to be in the future, right? So you're so you don't have to worry about anything about the past. Yeah. Is it deterministic? Okay, so well, the Markov chain we're describing a random process here. There's a probability, so transition matrix. But if we set it up correctly, which is what the next section of the talk will be about, or the lecture will be about, then there will deterministically be a limit that we will care about that will not depend on the randomness. Okay, so is there a life lesson about the randomness of life or the determinism of life and free will? I won't comment on that. Those are very big questions, too big for this class. Okay. Okay, great. So what I want to talk about is when can we define the limit? Oh, yeah. So there are 2 ways, 2 kind of versions of a there are 2 versions of a Markov chain. We kind of touched a little bit on these. Okay, one is I'm going to only consider one state at a time. Okay, this is the version where Q0 or each of my Qj is going to look like, okay, where I have exactly one position where I'm in, okay, and so in this version, there's only one position I'm worrying about, okay, and so this is where I'm thinking like I'm actually moving around on the graph, and I'm in state B, and then probabilistically I'll choose one of the neighboring states to go to, maybe state C or A. But let's say I go to state C. Well, then I'm currently in state C. Then I choose the next way to go. Okay, and I can think about only being in one position at a time. Okay, and you can actually run the Markov chain in this way. You can implement what is the limiting state of things by a Markov chain. Your simulation probably used the linear algebra approach, which is not really doing this. This would be like if I were building a state machine and I'm only in one state at a time. And then I want to kind of understand if I walk around, I can keep track of the distribution of all the places I visited, and that distribution gives me the limiting behavior. Okay, we'll talk a little bit at the end of the lecture how to think about this version. Let's be a little bit careful about it, because if you start counting your distribution from the beginning, your initial state can put bias into that distribution. You have to wait a while before you start counting, and then actually you might not keep track of every state. You may want to take a few steps before you add another thing into your distribution, because if I'm in state A, well, then the next one has to be one of the neighboring things. So I want to walk around a little bit before I take another point in the distribution. So it's a little tricky to do this one, but this is, there are some settings where this is all you can actually do. You can't actually use the linear algebra. With graphs, you can typically use the linear algebra, and now I can think of a probability distribution as the state. Okay, and this is the example of the state Qj equals something like 1/3, 0, 1/2, 0, 0, 1/12, 1/12, 0. Right, so it could be something like this. Again, this has to be an element of this space of the probability distribution. So all these values have to be between 0 and 1. They have to add up to 1. So it represents a probability distribution. But I can maintain this kind of distributional representation of where I am on the graph. So I think of all possible kind of universes at once, and I can build a distribution over these universes. Yeah.
This is a quick question. Would Markov chains also work if a node has an edge to itself?
Yes. This is totally fine. Yep. You can have a self loop. Everything we'll talk about, I'll give some examples where this happens as well. Right. Yeah. And in fact, for the modeling we'll see on Wednesday, this happens all the time. Yeah. So then you can go from a state back to the state itself, and this allows you to accumulate or keep some probability distribution in that state. Right. In fact, by doing this, you prevent some of the worst case behavior by adding some of these. That's one way of handling it. Great. So in your homework, you will actually implement both of these versions. Again, this one, if you're hopefully at this point you're not afraid of the linear algebra in this class, this one will be much easier, right? Because you can use the linear algebra. This one is if you've only seen like automata before, which when I probably first started teaching this class, this was probably more familiar to people. Now hopefully the linear algebra is like, okay, that just makes everything easy as long as your scale doesn't get too big. Okay. So, but again, what we want to understand is this limiting state, okay, Qn as n goes to infinity, right? Remember, Qn equals p to the power n of some initial state, Q or Q0. And I can, I probably would not, we'll eventually get to talking about it. I probably will not implement it this way, where I write p to the power n. Okay. But this is mathematically equivalent, right? So I want to understand as n goes to infinity, what does this state Qn look like? Okay, and the problem is that it does not always, the limit does not always exist. Okay, so I cannot always define the limit, and this is problematic because I would like to, I'll show you that this is a very powerful quantity to use if this does exist. It will say a lot about the structure of the graph. In order to get it to exist, I need to define a notion of the Markov chain to be ergodic, okay? And if it is ergodic, then the limit exists. All right, so then the limit exists, and I can use that vector as output to tell me a lot of stuff about the graph. Okay, and so I will say that the Markov chain is ergodic if, and so this is kind of the formal definition, if there exists a value t, okay, this will be the number of steps, okay, so that for all n greater or equal than t, Qn of j is going to be greater or equal than 0. This is to be true for all j in V. Okay, so this definition is probably a little bit to wrap your head around. So if there's some number of steps in the future where, and this should be from any starting position, if I take t or more steps, then at every point after that, for every n number of steps larger or equal than t, there's a positive probability of being in every single state. Okay, so this is the property technically which I need, and this is typically how it's defined. This is not that easy to work with, to think about, okay, I have a graph, does it have this property? Okay, so I want to explain to you that the Markov chain is going to be not ergodic if and only if one of three conditions happen. It can be more than one of these, but there are three conditions that can cause it not to be ergodic, and we can just rule out these three conditions. Okay, it's not ergodic if it has what are called absorbing and transient states. Okay. 2, if it is disconnected. Okay, this one is easier to understand, but we'll go through some examples. And the third one is that going to be if it's cyclic. This is this loop sort of condition you were talking. Okay, so we're going to go through and define these through examples. And I think they will be clear from seeing these examples how to check if it's going to be ergodic once you understand what these three cases are. If you rule these out, then you know it must be ergodic. then the limit must exist. And then if we do the linear algebra independent of our starting position, we will get some nice. Yeah. No, right? So let's go back to this example here. Let's say state Q3. I started in state B, right? And that's what this told me. And after 3 steps, the probability of being in state H is 0. All right, let's look back at the graph again. Oh, it should be strictly greater than. Yeah, I started in state B. I can't get to H. 1, 2, 3. So I can't get there. Yep, let me fix that. Thank you. That's a typo on my part. Okay. No, that was the wrong one. Okay. Good. Thanks for paying attention. Good. Okay, strictly greater than 0. Okay. Okay, great. Yes, this is a good point. They always have to be greater than equal than 0, but they have to be strictly greater than 0. Has to be some probability of being in every state from that point forward. If the Markov chain satisfies that for any initial condition, then it's going to be ergodic. Then the limit will exist, and then we can talk about how to compute the limit. Okay, so let's go through absorbing and transient states, disconnected, and the cyclic behavior here. Okay, I've got 3 examples of, I guess I'm starting with the, I've changed the order from what okay, we'll start with this cyclic examples. These are kind of the most kind of maybe unintuitive here. Okay, so let me draw these graphs, right? This is state A and B. And so I can think of drawing this as a graph like this. And now I don't have these, they're not from adjacency matrix, but I have to draw directed graphs here. So what happened is A is always going to B, and B is always going to A, right? This entry here is this edge here. Okay, and so this cyclic example is an example where there's a cycle and I must stay on this cycle, right? So I'm alternating between more than one state, and I can't break out of this pattern. If I start in A in step 1, or let's say step 0, I'm in A, then every even numbered state I'm in step A, and every odd number step I'm in step B, right? It doesn't have to be of even and odd. I can look at this next example here where I've got A, B, C. Let's look at this example. I have A here, B, and C. Okay, and A is always going to state C, right? So this edge here, described here. C is always going to B, and B is always going to A. So now if I start in state A, then every third step, I always have to come back to A. So this step 0, step 4, step 7, I'm always back to A. Okay? So these are not, don't satisfy the ergodic property, because the probability of being in state A at step 27 is going to be 0. I'm only if I look at the number of steps mod 3 in this case, that if it's 0 mod 3, then it's if I got that right, but it's the probability of being there is going to be 0, but in step 28, the probability is going to be 1, right? So I have I have my probability is shifting around, and it's never it won't ever converge. It will cyclically move around, and the convergence gets really messy. Yeah. So it depends on the initial state where I will be after some number of states, right? So that it means it depends on the initial state. I can write down exactly what the probability will be at some future step if I know the initial state, but I don't want it to depend on the initial state, right? So this there can be much more complicated ones. This is an interesting example. Let me go through. Now I have A, B, C, D, E, and F. And what's going on here? Well, I think hopefully it'll help if I write it in this way. A and F, and then B, C, D, and E. Okay, and so now A can evenly go to B, C, D, and E, right? And F can also has the same property. And then these all go back. They're equally going back on the same edges, basically, right? B can go to either state A or to state F. All right, so what sort of graph is this? Yeah, this sort of graph is called a bipartite graph. Okay, and so it has two sets of vertices, and it alternates between this set AF and the BCDE set, right? So it's hopping back and forth between these, and it's a cycle of length 2. Okay, whenever you have a bipartite graph, importantly, there are no edges within the AF side or within the BCDE side, only in between the two. That means it's got the cycle of length 2. So if you have a bipartite graph, it has the cycle. So it can be much bigger than a simple cycle like this, but it has to look like this. Okay, so these graphs are not going to be ergodic. Yeah. Even if I started with an undirected graph that was bipartite and I did the probability transition matrix, I would get exactly this. Right? These I have to define in a way which is directed to get them. Right? Otherwise, I could go back. Right. Well, actually, this one, this could be probably transition, but this one could not be. Yeah. That's correct. Yeah, I can even make one that's tripartite. Right? You just need no edges within your group and only edges across into the other groups. Actually, no, if I started with a tripartite undirected graph and I did probably transition matrix, it would not be cyclic, because I could go to either of the other two groups every step, and this would mess it up. All right, so if I have this graph and if I add a self loop onto it, right? So if I added some probability, say 0.1, and made this kind of 0.9. So there's a 10% chance I stay, or even less, that I stay at state B, and a 9% chance I go to state 9. Is this still cyclic? This is no longer cyclic if I do this, right? From A, I always go to C. From C, I always go to B. For B, most of the time I go to state A, but sometimes I stay in state B. And this breaks up this pattern where I have to hit A every third step, but I can't hit it anywhere in between. Now there's some chance I can do this. Even if this is 1 out of a million, it breaks it from being being cyclic. Okay, so it's cyclic. It has to only stay on that cycle, on the regular cycle. So if I have a graph that combines together a cycle of length 2 and a cycle of length 3, but there's some kind of connection in between these, doing this is fine. That's not cyclic, because walking between the cycle of length 2 and the one of length 3, if they're connected, it means that I can get anywhere at some point in the future. Okay, so cyclic has to only be cycles of the same length, and that's the only thing I can do. This is, if I have two separate cycles that are one's a state 3 and one's a state 2, this is still a problem, but that would be problematic for a different reason. We'll see next. Okay, the next case we have to worry about are these absorbing and transient examples. So what's going on here? Again, this is A and B. So let's say I have A here and B. What happens is half the time I go to state B, and from A, half the time I stay in state A. Okay, this self loop is okay here. But then what happens in state B? Well, I'm going to stay in state B. I'm going back with a self loop, right? This one is the self loop. And so if I start in state A, okay, half the time I stay in state A and half the time I go to state B. But once I get to state B, I don't, so I'm never leaving, right? So this is like this is like the Hotel California. Okay, so once you get there, you don't ever leave. I could have quoted that a bit better. But so like once you get into these absorbing states, you can't escape from them. Okay, so if I stayed in state A, do I always get to state B? There's some probability I stay in state A, I guess, right? But this is dropping exponentially, right? So from a kind of a limiting sense, I kind of always go into B. But there can be weird things where the limit, so the limit in this case is actually defined no matter where I start. I'm always going to be in state B in the limit here. But there are other cases where this might not be true. Let's see what I have in this example where A, B, and C. So A, B, and C. Okay, A always goes to B. B always goes back to A. And if I'm in C, I also always go to B. Okay, so what are the are the absorbing states here? So the absorbing states are going to be the combination of A and B. So in the limit, I'm going to get into A and B. If I start in C, I will initially move to B, and then I'll be between A and B. And then there's also this cycle inside of A and B, which is also causing this, causing these other problems. Okay, so this is a really kind of messed up situation. Again, the limit will always be between A and B, but this is a cycle again. Okay. Okay, what's happening in this other case? A, B, C, D, E, and F. Okay, of A and B, and then C, D, E, and F. Okay, between A and B, A half the time it will go to B, and half the time it will stay by itself. Okay, that seems okay. B, half the time it will go back to A. Almost half the time 49 out of 100, it will come back to itself. But 1 out of 100 times, it will go to C. And then once I'm here, then it will get in this state where it will, great, I have fully connected graph down here at the bottom. Right, so if I start in A, half the time it'll go to B or stay in A, and then 1 out of 100 times, it will leak out a small amount into here. And once it gets into this section down here, it's absorbing. There's no way it can leave out of this state. Okay, so then if those are called the absorbing states, then these are called the transient states. This would be transient, and this would be the transient states. The transient states are the ones where, okay, I can start in there, but eventually all the probability is leaking out of them. Okay, and so in order, so these again, the limiting time condition here, it can be messed up. Well, let me give another example of why this is hard. Let's say I have states A, C, and D. Let's see, D has a self loop to itself. C has a self loop to itself. A goes to C 1/3 of the time and to D 2/3 of the time. If I start in state A, now there are two different kind of absorbing states. And depending on this initial condition, or what I do at this initial RAM thing, I either end up in one or the other. So if I model this as a random walk, if I do this in the way where I'm making one step at a time myself, well, I could end up in one of the two states and I will always stick there. If I do the probability transition with the linear algebra, well, then I will be 1/3 of the chance here and 2/3 of the chance here. Okay, and this is maybe kind of the right answer. But if I started in D, then I always stay in D, right? So if my initial state is D, I will always stay in D. If it's in C, I always stay in C. So it depends on the initial condition, and it may actually depend on the random choice, depending on how I'm actually modeling it. So that's why these absorbing and transient states are kind of a mess about dealing with the limiting behavior. Okay, so this, you also don't want this sort of behavior, because I mean, one of the reasons that I would like to know something about maybe a complex absorbing state here, and to model something about it with my limiting distribution, the limiting distribution will tell me nothing about this. And I would like to know what's going on up here, not just that everything leaves, right? So we'll see when we're modeling the web graph in the next lecture, actually most of the web is going to actually be absorbing states if we're not careful about it. So most of what we want to model, is transient states, is the transient states. So if we just run this without doing some like careful things, we will have no information about most of the web, and everything will fall into some absorbing states, which will be not very useful to us. Okay, let's quickly go through these last examples. These are unconnected examples. This is where A and B, A is a self loop to itself, B is a self loop to itself. So if I start in A, I'm going to say in A. I could also have this example A, B, and C, where A, B, and C. A is always going to go to B. B always goes to A. That's playing nice with each other, but C is left out by itself, right? So I cannot get from A and B into C. So these are not connected, and this is a more complicated example, right? Where A and B are connected, C, D, and E are connected, and F is off by itself. Okay, so these also I don't have this limiting information. All right, okay. So if I don't have one of these three conditions, right, the cyclic behavior, the absorbing and transient, and if the unconnected graphs, then it's going to be ergodic, and I can talk about this limit. Okay, so I can say if the Markov chain is ergodic, okay, then I can talk about the limiting state, and I can say both what happens to the probability distribution in the limit, the kind of the probability transition matrix in the limit, P star, and the state Q star. It's going to be more interesting. So then I say, what is this? If I look at probability transition matrix Q star, it will tell me from any initial condition, right? So for any initial condition, I get the same Q star. Okay, so I get the same state. Okay, and so this was your life lesson number 2. Just worry about one step at a time. You will get there eventually, or you won't. What would happen if you won't? You may not get there eventually if you're not ergodic. Okay, so hopefully, so all of you are ergodic individuals, I guess, unless maybe the absorbing state's not a good one, then maybe it's okay not to be ergodic. Okay, so this tells us lots of nice things here. Okay, so there's one of the properties you get is called this delicate balance. Okay, and so what this is saying is that if let's look at this equation I've written here, right? So if I start, so I also have this equation because I can, so, well, there are a few ways to see this. P times P star is going to be the same limiting distribution. So if I start in any state, P star times P gives me back Q star. Okay. But it also means that this term here is Q star, right? So then I get this equation here. Okay, so this equation only depends on P, not on P star. So what does this say? It's saying that if I'm in state Q star and I apply this matrix, I get back Q star. What does that say about Q star? What linear algebra property does it exhibit? Identity. It's an eigenvector. Yes, great. So this means Q star is an eigenvector of P. Okay, and in fact, it will be it'll be the top eigenvector. Okay, so in fact, if you remember the power method, how to compute the eigenvector, this just describes the algorithm for the power method. Okay, so it's an eigenvector of the matrix P. Again, this is P, this is not P star, right? So I take the original probability transition matrix, and its eigenvector is the limiting distribution Q star. Okay, I also get this property called this is called the delicate balance. Okay, and it is, okay, so the probability that I'm in state I and transition to state J, that's going to be equal to the probability in state J and transition to state I. Okay, so this is saying this I is here. The probability I'm in state J is here, and this is the probability transition matrix from J to I from being in state J, okay, is equal to the probability of being in state I and then transitioning to state J. Okay, so if I consider two states and I can look at, if I just look at those in the converged to state, okay, and I can just look at those two states, there's a perfect balance between them. The probability of being in one transition to the other is the same as being the other and transitioning back to itself. If that was not true, then those would kind of be leaking information from one into the other. So when I'm in this converged to state, every pair of states are kind of in perfect balance with each other. Not just the whole situation, but every pair of states even has this, right? So I have a lot of structure balance here. So it's kind of easy to this property is a very local property I get as well as this global property. All right, and I guess this is in the limit, everyone has perfect, so karma. So, all right, and I just want to, okay, so back to what I mentioned, this is not uniform. This is our initial graph, build the probability transition matrix out of it, converge, hopefully you got this, kind of the same answer here. I have a bunch of things which are the same here. This is, these states are all 3 out of 20. Let's see, this is A, D, A, C, D, E, F, and G all have 3 out of, no, not F. And G all have this same value. B and F have a smaller values, and state H has the smallest value here, right? Yep. F and G swapped. Okay. Okay, good. Yeah. Oh, okay, so the fact we have so many ties is a little unusual. This is a smaller graph, and bigger things, it's may not converge to such nice things here. But what you see are the blue nodes are much more central. And if I do a random walk, I'm gonna tend to be in the middle of the graph, and I'm less likely to get out on the tails. All right, and that's a very small probability of getting out on the tails. In order to get from the central part, the blue part, which is kind of central, to get out here, I have to get here from state F, right? But if I get to H, I always go back to F again. And from F, then I can leave to get back to the central part, but it's hard to get out to H here. Again, B and G are kind of off to the side. They're similar, kind of, I can only get to them from 2 states. And if I leave after I'm here, I leave back into the more well-connected part of the graph again. Okay, and so this is kind of the states, the probability distribution here kind of tells me something about the graph, about which nodes are more central, which nodes are more on the periphery. These are going to have some lower values here. Okay, great. Okay, so 2 ways let's talk about algorithms for computing Q star. Okay, there are a number of different ways you can compute it. So I can take the eigenvalue of P. So I can take the top eigenvalue V1. All right, but this is going to not be the final answer. It is a normal vector. It is L2 normalized. The eigenvector is typically given as L2 normalized. So then Q star is equal to, I need to do an L1 normalization of it to get it out. Okay, this is probably the easiest way to do it. Okay, but how does this eigs computation that you call, how is that actually implemented? Is it magic that it calls? Well, it's probably doing something like the power method, where you just multiply by this probability transition matrix over and over again for n steps, for n kind of large. This is called the power method. And this is probably this is one of the most common ways how to compute it. There are other ways they're more numerically stable that might be a bit better than this. But for just the top eigenvector, this is a pretty good algorithm. It's especially good because the matrix P is typically sparse, right? So when I multiply a vector times a matrix on a sparse matrix, I can do this pretty quickly. I don't have to it's not as slow as a dense matrix vector product. It's a sparse matrix times a dense vector, which if the matrix has about a constant number of items per column, then it's linear time per step. Okay, so I can do this fairly quickly. Okay, the third way is to compute Pn, okay, which is P times P times P. I don't have to necessarily multiply this n times. I can actually do P squared times P squared, and then I can do I can square this, and then I can square this, and so forth. And this only needs log of n steps. Okay, so I have to square the matrix log n times, I can get P to the n, but this will be a dense matrix. So even though instead of n steps, I need log n steps, it's a dense matrix, so it's most of these are pretty slow operations. It will get dense pretty quick. Okay, so this is not that common. And then the fourth way is the actual random walk. Okay, on P. And then I want to keep track of the distribution. Okay, so I have an empirical distribution I keep track of. Again, this you have to be careful. You typically do a burn-in period where you first take a bunch of random walks to get to a random state because you don't want to start in the corner. That will bias your distribution. And then after every step that you keep, you may want to take some number of steps before you count the next one. In practice, that second part is less common to do, but the burn-in period is very common. And this is you should almost always do this. Because if I started, imagine a graph that had an even more extreme section over here. If I started there, I'm going to walk around in there before I escape, and I will know that will be part of my overweighted in my distribution, unless I walk for a huge amount of steps. I'm better off starting until I get to a random position and then do the random walk, and then it will give me an unbiased estimate. And kind of how many steps you have to do for this is kind of unknown. You kind of know once you do it if you did it long enough. It's kind of unsatisfying. There's been a lot of work in trying to figure this out. Okay, I have 1 minute left. Let me just tell you, there's this thing called the Metropolis algorithm invented during these are all people who worked in the Manhattan Project, if you saw Oppenheimer. And so this is to sample from this can work if you're sampling from a continuous distribution instead, where I start at a state, but the state can actually be a point in some continuous space. And now I can pick a random neighboring point from like a kernel. This can be like a Gaussian kernel in the space. And then I have a weight. The weight is often defined on some like statistical physics. And I look at the energy of the state. And basically, if the energy of the state is decreasing, right, then I need less energy to be in that state. I'm more likely, I'm always going to accept that random move, right? If the energy is decreasing, so the weight is increasing. So this isn't could be thought of as a likelihood of being in that state if I'm using this for Bayesian inference. But if I move to a state with a lower weight, then I look at the ratio of the state I was in and the ratio of the state I'm planning to move to. So now this is smaller than this one. So this is a probability, and I move to it with that probability. Okay. What this will give me is if I run this algorithm, and if not, then I stay in the same state. If I run this algorithm and I pick the random walk kind of distribution at the end, I will generate random samples from the probability distribution where this is the likelihood, where I don't need to know how to normalize that probability distribution. I just need the likelihood. And in Bayesian statistics, you often don't know how to normalize the distributions, but you can evaluate the likelihood. And so this is the workhorse of Bayesian statistics. And you can't do this by maintaining this quantum state. You have to be in one position at a time to do this because you're in a continuous distribution. You couldn't, the length of the vector would be infinite. So you can't keep track of the whole vector here. So you have to kind of keep track of one state at a time, but this will give you an approximation of the distribution of the state for this. And so if you do take the probabilistic machine learning class, which hopefully we'll offer again next year, then you'll use this to kind of understand all sorts of kind of Bayesian statistics for things in machine learning. Okay, great. We'll stop here.